First off, thank you very much for coming today. We know your time is valuable. This is our first effort to bring together a community of folks, developers, people from the industry. I think you'll find that the group that's been assembled today, there's a lot of synergy between your areas of interest. Just this morning, as I was chatting with folks in the hallway, there's relationships here that clearly we hope you have the opportunity to take advantage of. So one of the things I'm going to talk about today is this concept that I call the Internet of Machines. And it's a term that you might think is sort of obvious, right? The internet isn't a fact, interconnection and network of machines. But I really want to paint a picture of the world that we see coming that's a direct product of the Internet of Things and all of the data that's being produced that we have to process. And it's interesting. So today we have of developers, right? Many of you are in the software space. And I'm going to talk a little bit about the hardware and the trends that are driving this. And I actually believe it's a very to be in software because I believe we're at a point where we're transforming the way we build software and actually connect that software to the machines that are actually going to be doing a lot of the work for us. And you'll see this theme manifest through a number of the presentations today. And so, as Leo mentioned, we have an outstanding lineup of leaders in the technology space, both in software and in hardware. And we really hope that this event today sort of is illuminating and productive for you. So, again, we also invite your feedback throughout this process. We want to make this an event for you. It's not really about Nimbix. It's about this community and about the vision and that we hope we all share together and how we can help create this future. So let me go ahead and start by building a story, I guess, and that sort of conveys my view of where I think things are going. And I want to start by talking about Moore's Law. How many of you are familiar with Moore's Law? So pretty much most folks in the room. So the idea that the number of transistors on a semiconductor chip doubles every 2 years approximately. And this has been, as someone who came out of the semiconductor industry, when I came out of college, I went to work for Texas Instruments. And so we sort of lived by this idea of Moore's Law, and it was woven into our DNA. Interesting to me is not Moore's Law in and of it. Today about Moore's Law being alive or dead, and we all have some opinions on that, and we'll talk about that more. But to me, what's interesting is the doubling of transistors every 2 years has had profound effects on many other things, aside from just the sheer technology prowess of being able to shrink transistors on a die. And the first is we've been able to computing and democratize access for software, or democratize software development as a whole. There is a time in our history on a machine was not accessible to everybody. It was a very expensive proposition. And so part of the effect of Moore's Law has been to open up this to write code. The other area that to me is extremely important relative to Moore's Law is economics. And I talk about this concept of predictive comfort and this idea that the entire industry, every equipment manufacturer that builds something that uses chips has this predictive comfort of knowing that we're going to have double performance and capabilities that we count on. We know that our processor companies, our silicon companies are going to give us these new and step back from this because we've thrived off this for over 3 decades of Moore's Law, actually 50 years of Moore's Law being followed. And so it starts to beg the question that what happens if this predictive comfort goes away and we have to think about different things. Let's look at state of the art. generation had 1.5 billion transistors at 22 nanometers, which is the current process node. And back when I was in semiconductors, we were in microns, not nanometers. And so obviously it's, but we know that at 7 nanometers, we start to quantum effects of being, that small, where even a single atom that gets in the way of your process is going to have an effect. It's probably take longer than the 2 years predicted by Moore's law. So, and again, to me, it's not so much can we double again and can we double again, as much as we know that at some point we are at the atomic scale. And at that point, our current semiconductor technology has to change, right? It can't continue the same path because of the atomic scale. So the question is, are we at the end? And I would argue that we certainly have, we're seeing a world that's going to be changing, right? How Intel, as recently as January, in a blog post that was on HPC Wire, said that Moore's law is just fine. There's no issues with Moore's law. And in fact, it's alive and well. We're going to the next node, which they are. There is a roadmap beyond down to the single nanometer mentioned. And whether or not it's true or false is less important. I mean, if we are at the forced to think about things differently. One of the points, and it goes back to economics, talk about is Moore's second law, and it's also attributed to Arthur Rock, which is the inverse of the first law. And the inverse is that the cost of building the wafer fab plant for a new process generation also doubles every node. And so you have this growing cost associated with the next generation technology. So that if you're Intel or IBM or the folks that are doing transistor design, that's an important reality, right? It's an economic reality that starts to beg the question. We can't get to look at what these chips are designed to do and to be able to actually deliver what the market's demanding. We also know, this has been sort of a foregone conclusion for many years now, that clock frequencies can't get faster, or that gone are the days when we would introduce a new chip and of performance just out of the box, right? Software doesn't have to change one bit. You get a big performance boost and everybody's happy. And so what's happened, and we've seen this when we've moved into the era of multi-core and sort of heterogeneity of architecture, we see erosion of the predictive comfort. The market is sort of tussling about what comes next, what comes after what we've been doing for 50 years. And the very question is forcing, in my opinion, innovation in new areas. We're in specifically, I believe that we're seeing a deeper focus on the applications and the functions that these applications are demanding as general purpose architectures. And we're going to have the silicon real estate to start to explore this. So our conundrum at this moment as developers and technology workers in this ecosystem, at the very moment that our chips stop getting faster, we have this tremendous explosion in data that we have to process, that we want to process. And we want to process it to help us solve problems, to introduce new services, able to scale and tackle all of the things that the complexity. We have a number of different application domains that are extremely demanding. And by the way, this is not new. Having applications desiring different capabilities in an architecture is not a new thing per se, but it's clear that in these domains, there are particular compute requirements that might be favored in one application domain versus another. For example, some applications may want lots of traditional CPU cores, whether it's x86 or some other type of CPU core power CUDA GPU cores. Some applications demand significant amounts of memory. Some applications want different flavors of floating point, single precision, double precision, and all of these things impact what solutions are brought to market. And the exercise at the semiconductor company level is always about how big is the market for us to go make an investment in a new chip that's going to solve these kinds of problems. And what's interesting is that the general purpose architectures of the past many years are not quite getting us there when it comes to the specific demands of these application domains and what they're expecting of infrastructure. So when I talk about the Internet of Things, I use the term data transformation. We could also say data processing. Data is in there as well. But the idea is that we have these billions and trillions of attack devices to the Internet, right, that are producing troves and troves of data. We're going to hear later in the life sciences about these sequencing machines are now attached, and they're just spewing out terabytes and terabytes of data. We have to then think about what useful things do we want to do with. How do we analyze that bucket of information, or how do we transform that data to get some answer out? And when I talk about data transformation, for me, it's transformation is all computation, right? We may be, transcoding is an example of what I would view as data transformation application. You're taking a video stream, you're doing some operation, and you have an output. And that really apply to simulation, a number of different domains, versus analysis, where you may be taking a collection of data and then doing some kind of analytics to understand or glean new information from that. And the idea here is that we want to produce results from the transformation. We want to gain new insights or new knowledge from understanding and transforming that data, or provide some service in the transformation. Later this morning, you'll hear from Paul Arden and MyGenius, and one of the applications there is real-time photorealistic rendering, where it's really a service as the output of the data transaction or the set of inputs. And so this is the world that we actually live in today, and what we're in the midst of, in my view, is transforming and accelerating how we can actually tackle the demands that are going to be thrust upon us through this model. So what are the demands of this paradigm? I would argue that one of the key demands is real-time answers, or very near real-time answers. And I use the example of thinking about internet search, what Google has done. You can talk to your phone, your speech is recognized, and then your search is launched, and within milliseconds, you have your response to that search. And this is the demand of one use case, is where we expect instantaneous answers. From a simulation perspective, we are now simulating, and we desire to simulate whole systems, not just samples or a subset. And I take the example of gaming, right, where actually NVIDIA is doing multiple simulations in real-time fluid dynamics with smoke, water, explosions, and this is all being computed real-time on the fly. And this actually has an exponentially increasing demand on computation. And then finally, the world requires this to be distributed and mobile access from any connected device to be able to affect these sort of transactions or these computations or data transformations from the data that we have access to. So in my view, if we were to argue that we're approaching the end of Moore's Law, or have arrived at Moore's Law, that it's driving the adoption from a software perspective of new architectures. Now, we've had alternative architectures for a long time, but we're finally seeing a point where the economics and sort of the tipping point of driving new architectural evolution is being thrust upon us. We want to do things like attach accelerators to specifically help boost application performance in specific domains. We want power efficiency in the data center So we're not just adding more energy to the equation. We actually are being smart. Data streaming architectures where you're in real time and doing some kind of analysis or transformation on that, or core density for parallel computing applications for the computational aspects of a given set of problems. And we see this in the market right now, right? We see these co-processors. We're going to hear about this technology throughout the day today. And these are the people that are driving this technology. And so what I hope is that one of the big takeaways from today is that this isn't sort of an understood domain, and that the tools are arriving for software developers to take advantage of this right now. So I want to talk about just a couple, and you're going to hear a little later today in some of the other presentations a little bit more detail here. But one of the more prolific co-processing architectures today is attached GPUs. And this has really been driven from the massive presence of GPUs in the gaming world. But because they were designed to do image processing, a specific application really well, we've been able to apply that to a whole host of other problems. And historically, Moore's law at work for NVIDIA, as an example, applies to AMD as well for their GPUs, is you can grow the number of thread cores, CUDA cores on a given device, which then in effect translates to more parallel processing power. And so we're going to see, again, NVIDIA is no different from Intel, IBM, or anyone else in terms of the challenge of what comes after, the next process node. And then the other thing about GPUs is for specific applications, you can see significant speedups relative to CPU. So it's an alternative architecture to a general purpose CPU-based approach to solving a given problem or set of problems. Where I want to spend kind of the rest of the time building my thesis around the Internet of Machines is with respect to FPGAs. So just a quick show of hands, how many of you are familiar with FPGA hardware? Awesome. So the idea with FPGAs is you literally have a blank slate of silicon that you can put whatever you want inside of to affect your computation or your specific function in some way. And Moore's law at work historically in the FPGA world is growth in what they call the logic gate count, the ability to put more and more complex functionality into these chips that has sort of been one of the limiting factors historically on FPGAs. These have been very, very big, important components in the communications industry, and we're seeing, in my view, sort of the entry point of a revolution in the computing industry with the presence of FPGAs. And this is evidenced in some respects by Intel purchasing Altera, one of the other, we have Xilinx here today, one of the other FPGA companies for $17 billion. So that sort of implicitly makes a statement about this. And then I make the comment about their traditionally expensive devices only to suggest that the economic equation is also really important, that we're seeing now that as you reach the end of traditional process technology, what that means is you now have, you can sort of reorient to thinking about what do we do with that silicon real estate? What can we put in it? And the innovation trajectory becomes more about what to do in the silicon, and that drives cost down, which means we can now start to see a more widespread adoption of this kind of technology in the computing world. So I'm going to segue now just a little bit, and then I'm going to come back to this to sort of draw my conclusion, and you guys can, believe me or not, or whatever, you'll be able to form your own opinion. But hopefully, I will communicate successfully the vision and sort of the view that we have on what comes next. But you're going to hear also specifically about the application of machine learning today. And obviously, this is an area for those of you in the Python community that you're probably seeing this in the data science world significantly. But one of the reasons why we're seeing this emerge, and it's, in my view, no coincidence that it's emerging around this sort of time of transformation, is that we need some automation to help us chunk through all this data. And not just automation, but actually applying some intelligence. We have all this data. So let's train machines to help us chug through all of that data. And an example here is when we take, for example, labeled data like a facial image, right? And we say this is a face, and we train a machine to recognize a face. And now you can feed it new information, and it can tell you if it's a face or not, or even who that face is. We can also apply unsupervised learning to assemble unstructured data. And this is really important because I think that there's a lot of information we don't even know, or knowledge we don't even know exists. It's there, but because we don't have the capacity to process the petabytes of data to create structure or categorization of data, unstructured data sets, we can teach our machines to help us do that. So the other thing that's interesting to me here is that this is evolving very rapidly, and in a large sense, it's due to the availability of cloud computing, the ability to scale out to help pretty much any developer leverage and create a data model for us to do and teach machines learn. But today, we see a lot of use in the image recognition space, speech. Of course, Google's been using this for a long time, and in fact, their application of machine learning to help them get more accurate speech recognition has, in some extremely short amount of time, sort of exponentially improved over the first 30 years of technology and development in the area of speech recognition. And then, of course, recommendation engines, just smarter tools for helping sort of understand a consumer and their behavior and kind of their history and so forth. That's a part that can be a little bit scary. But overall, it's helping the market move very quickly. Now, I'm not an expert in machine learning by any stretch, but I want to talk briefly about the different learning models that are out there. Obviously, supervised is the comment I made, where we can take a set of labeled data, feed significant amounts into the training process for the machine, and then use that to predict the output from a set of unlabeled inputs. On the unsupervised side, this is where we don't know what the inputs are, right? This is this idea of unstructured data or some collection of data that we can then apply a data model to, and then understand something interesting that comes out of that data. These can have deeper layers of hierarchy than a supervised model, and can have, I guess, additional abstraction there. One of the other models out there is the reinforcement model, and when Dennis comes to talk as our resident machine learning guru, I'll have some questions for Dennis. But this is sort of the game theory approach, right, where you can teach machines with a set of rules and rewards what actions it can take, and then what end states are desired. And so this is just an interesting, and has been deployed in as well understood mathematical models, but a lot of the sort of the AI, right, research is gone on in each of these different learning models. And so specifically, on the reinforcement side, again, as I stated, you have a set of environment states, actions that a machine can take, what can it do transitioning between states, and then how is it rewarded, and then let the machine, the model or the algorithm start to take hold, and let the machine start to actually learn from their environment and how to best make decisions on the inputs that it receives or the states or environments that it's in. So now I'm going to kind of segue back to the idea of programmable devices and sort of the IoT and the collection of machines. And let's apply machine learning to reconfigurable silicon and data processing as a process. We have access to millions of API calls. And here, when I talk about an API call, let's consider the actual task as the API call. So in cloud computing, a lot of times the API call is to turn on a machine or turn off a machine, or I want to construct some machines. In this context, the API call is the actual compute workloads describing, I want to render X, Y, and Z on this data set in this amount of time, go. right? That's kind of the concept behind this. We can create in the Internet of Things millions and billions of these API calls that can be fed to train machines on how to best process them. And you can actually define those rules that you wish to optimize around. So we might want a machine to say, let's look at the most energy efficient way to process this payload. Or let's optimize for runtime. Or let's optimize for lowest cost. Whatever the set of rules for the environment, we can teach the machines to tune for those specific things. So the idea with FPGAs and reconfigurable silicon as a part, an integral part of a cloud paradigm, you can imagine when you take a set of workloads, whether those are grouped as labeled, rendering, or simulation, or NGS sequencing, allow the machines to define what the optimal way to process those payloads are. And even further, let the machines teach the machines what needs to be processed to begin with. There may be a set of things we don't know we should process, but the machines then can sort of develop an idea based on what we teach them of what should be processed, what data is valuable, what information might we produce new insights from. And this is really where you start to see the concept of the Internet of Machines in the way that we envision it, is where we can create significant automation to help us as humans process the information to help us solve the hardest problems that we can confront as a global society. So what we arrive at is what I call the engine room for the Internet of Things. So I think of it as the Internet of Things is the attached devices themselves. The Internet of Machines sort of sits around it and is the engine room to help us process all of this information to derive meaningful answers and solve complex problems. So think of it as intelligent systems that with reconfigurable silicon have the tools to self-optimize, to program their own bit streams, to be able to not just automate, but accelerate the distribution, collection, transformation of the massive amounts of data that we have. So, and I like the term accelerate because we live in a world of exponentials. And as we talk about all the time in the technology industry, we see the acceleration of kind of the curves that we're on. And these systems help give us yet another exponential component in accelerating how we can process information, which means, to me, we can cure cancer faster. We can solve world hunger faster. We can colonize Mars faster. We can solve transportation logistics issues faster. These are things that as our population continues to swell, there are problems and challenges we want to meet with answers faster than we could if we were on a traditional linear curve, which to me is what I'm extremely passionate about, is how we help accelerate our time to results, our time to answers to some of our most complex problems. So to conclude here, what are we at Nimbix about? In the Nimbix Cloud and Jarvis, and this is kind of the one sort of point I'll make about Nimbix today, what we are here to do is to help drive and initiate this transformation. So first off, for developers, we want to democratize access to these new architectures. We want to make it used to be very expensive, right? If you were a developer and you wanted to work on FPGAs, you got to go buy a $10,000 card, you got to put it in a workstation, you got to learn a tool chain, the tools are expensive, you have to learn the synthesis process and those tools. What we want to do is accelerate your access to building new code that leverages the capabilities of this heterogeneous environments. We also have a platform where we want to give tools to make production applications available for transforming and analyzing data. Meaning, once the applications are there to solve a given problem, you can scale it through the sort of the construct of the Jarvis API. And then finally, what we believe is that it is the first evolution of what we call reconfigurable cloud computing for hyperscale data processing. The ability to have a set of machines that can self-optimize at the appropriate time. And we're not there yet, right? We're at the first evolution, right? Let's introduce the concept, let's introduce the technology, put it in the hands of the community, in the hands of the smart people that can help write the code, create the algorithms that then allow us to evolve these sets of systems to help us process the data. So with that, that concludes sort of my presentation. We have a few minutes here that we'll have some time for Q&A, and I think that's the way we're going to run the presentations today based on speaker time, is if we have a little extra time, we'll try to answer questions, and of course, if we don't have time, we'll be able to ask and interact, at the break. So again, thank you very much for your time today. We really value it. We hope you get a lot out of the day today, and I will go ahead and take some questions. So thank you.
I'll come around and bring the mic, so don't be shy. Sorry.
So I'm really intrigued by this idea of putting a machine learning layer in between the problem in the data set and the compute, and with a platform like Java. So what needs to happen there exactly? You talked about the software a little bit, but I was hoping you could elaborate a little bit on what pieces need to be in place there to make that a reality.
Yeah, great question. And that is really, that's the question. And I'll tell you what I think it is, and I could be wrong. But that's why I'm presenting it all to you guys, is to help us figure it out. But what needs to happen is a couple of things. First off, first evolution is we're now putting FPGA silicon and GPUs, right, other architectures in the cloud to enable accelerated processing for specific applications. The next step is we need to build the data models that we can then train the machines around how we want to optimize. And this will be iterative, I believe, for maybe a while, right? We're going to learn, we're going to teach machines sort of one thing, and we're going to say, oh, they did pretty good at that. That works well for this niche or maybe some specific thing. But now we want to apply maybe another learning model, or maybe we want to use a reinforcement model. Whatever those things are, I think that's going to be iterative. And then once we have that template, right, this model, we can start to let the machines make some decisions about how we can tackle those workloads. Now, specifically with FPGAs and reconfiguring, there are some things that have to happen in the evolution of the tool chain, and we're going to talk today about some of what is happening right now to enable this. And the idea is that we want to compact the tool chain for taking code that a developer might write, and then taking it through an optimization process, and then the synthesis tools that are required to build, a net list for the FPGA to configure its logic for that given function. Now, we have the technology today to dynamically reprogram the silicon for a fixed function. It's that we can do that today in our cloud. We actually we sort of did a POC about 3 or 4 years ago on that capability, which was really cool and very exciting. We could take a workload like a life sciences, a genomics workload, and then the very next workload might have been a transcoding workload that's 100 times faster than it would be in a traditional commodity cloud using CPUs only. And that's the idea here, is acceleration and computation. So so that bit stream, that process of kind of compacting the flow of code and synthesis is we're speeding that process up. And once that's kind of compacted, you apply the machine learning to that, and then you iterate and let the model start to play out. That's at least our vision of how that might happen. Probably happen some slightly other way. There may be something else in there, but that's really what we see evolving over time.
So when you say machine learning, coming from a biological perspective, I hear evolution. And there's a guy named Adrian Thompson who did some circuit evolution with FPGA chips, and just to detect simple tones. And what his FPGA chips evolved into after several generations was something not recognizable, where there's disconnected logic cores that a human would never have invented from first principles. And I think that was something like that hasn't really been built on because it's hard to understand. Yeah. So I'm curious what where the division point is between how much, how you set your conditions. Because if you set your conditions too stringently, you might miss out on some really amazing stuff that you would never have thought to look for. But if you do it too loosely, you can get stuck in infinite loops. So I'm curious where that balance point is.
So my view on that is, and I agree, first off, on the comment of some of the research happening here. There's some amazing technology and research out there all around the world right now, but it's so, it's not visible to the broader community. One of the reasons why we wanted to have this event and kick this off is to sort of evangelize that idea, this concept, and accelerate its adoption into the marketplace. And that starts with really software developers understanding what can be done with these kind of platforms. So on the point of evolution, I'm a big believer that we're, and not to get too philosophical, but I do believe that machines will augment in every way the kinds of things that we as humans need to discover, problems we need to solve to do that. But there will be, and I think it's interesting, I was talking with someone about another AI company in London who's done some really interesting research in image recognition. And I remember we were relating stories, and 2 years ago, or a year and a half ago, at the supercomputing conference, I met these guys, and it was a young AI data scientist guy, and what he told me is that they trained their FPGA machine, and then it started producing answers that they weren't expecting, and it allowed that to play out. So I think that's actually one of the great opportunities here. Is that I don't know that there's a silver bullet answer. We have to explore, and allow the technology to evolve.
Thank you. You focus quite a lot on the processor side of things. I'm wondering how important you see the interconnect aspect of things, and whether the technology there is advancing fast enough to keep up with what's happening on the processor side.
Excellent question, and we agree, and I think also we'll hear later today some presentations that will talk specifically about different layers of interconnect. One of the things we've done, because we do believe that's very important, and we actually believe that today's interconnect in what I call the commodity cloud landscape is insufficient to enable this kind of processing. So what we've done in the Nimbix Cloud is we've pushed the state of the art, of course, working with our sponsor here, Mellanox, to provide the bandwidth and throughput between the systems in our cloud to allow for highly coupled processing, parallel processing. So, I honestly think that there's some innovations happening there in optics in different areas that are going to revolutionize even further the computational aspects. But I agree with you. This is an area we can't forget. And even, I think either IBM and Xilinx may talk about some of the interconnect topologies going on in open power with NVIDIA and NVLink. And of course, there's different protocols to do that. The market will ultimately help us adopt what's one of the options with respect to that. But it is something that has to co-evolve with the computational side of it. So, and there are some unsolved problems as of yet, I think there, so.
Okay.
So I was going to go with the same way. I'm going to take that one step farther. Besides the interconnect technology themselves, right, speeding that up, as you parallelize your compute nodes, a distributed data model becomes complex. You all want to see the same data. So how do you change the data flow through your system? Right now, most FPGAs are offload, right? Mm-hmm. The data still has to flow into your CAC and back out, and you have this one path. Is there any thought in your infrastructure to change that?
Yes. We are constrained like every other business based on how we invest and investing to what the market is demanding right now. We often, envisioned, we dream about what if we could build exactly what you wanted. Well, I mean, and that's true of so many, people and engineers. You want to build, I love the Elon Musk stuff with Hyperloop, right? And kind of opening that up to the community to kind of create and design and solve those challenges that if any one company by themselves, it would be difficult to make the investments required to do that. So we're constrained, somewhat by the business model, and that is a challenge, right? And I think I mentioned data streaming architectures, and there will need to be systems that can enable better sort of handling of data management through that process. Today, we do the best we can, right? And what we try to do is provide very low latency, high throughput, high bandwidth interconnect within a distributed data layer. So our cloud actually uses distributed data storage that is persistent, that can attach elastically to the compute with the high bandwidth that needs to stream into the systems. Now, from within the systems themselves, there are some constraints there, right, with FPGAs and offload device. So we're going to hear more about, you guys are going to talk about some of these interfaces and some of the ways that we can solve those problems. And I think that, we're excited to hear about that and how we can start to leverage those things with the particular use cases that demand it.
Anyone else? Don't be shy. So far, he's answered all of your questions, so feel free to keep asking. He's not dodging them.
Yeah, when I start dodging them, then
then we'll just cut it short. Yeah.
Yeah.
Anyone? All right.
All right.
Well, thanks very much, Steve.
Thanks.